Hi, my name is Corentin and I will present you our work on scalable multiclass sampling via filtered sliced optimal transport. I will start by quickly introducing the multiclass sampling, then I will present our framework and the practical optimization method. Finally, I will make a focus on blue noise error distribution in rendering and the link to multiclass sampling. So first, the multiclass sampling. Let's take this 2D example. We want to be able to colorize the point and maintain a good quality for each color. Each color here of point is a class, and the union of the two colors is also a class. This makes it a three-class problem. Generally, multi-class sampling is used in various problems such as object placement, surface reconstruction, or image stippling, and many other problems. Now, let me present our scalable multi-class framework and how to use it to construct classes. We start with a point set here on the 2D domain that we will simplify as a vertical flatland on the right for the visualization. We can now introduce a second dimension to the problem that will classify the points. The idea of this new dimension is to create an index space, and if you think the point set as a list of points, this new dimension simply represents the index of the point in the list. In order to create a class, we need to select a range of points from the full set. Let's take this region as example defined by a box function. As you can see, it creates a selection of points in blue from the full set. It is possible to use even more complex function than a simple box. For example, a staircase shape function. As the difference to the previous example, here all functions show two different levels. In practice, it means that the point under the big step belong at 100% to the class, and the one under the small step only at 50%. You can see that we have two different levels of blue in the point set on the 2D plane. This notion of belonging in a non-binary way to a class is new to our paper. We can also use even more complex class functions, such as discussion. Nevertheless, practical optimization methods generally need a binary point selection for each class. This is the reason we introduced the concept of subclasses. A subclass is a filtering of a class leading to a binary selection of points. To do so, we first select a thresholding value, here visible as the horizontal line, and the subclass consists of all points of the class for which their value is greater than the threshold. By testing every possible threshold value, it will create every subclasses for a given class function. Note that the point with high value in the class appear more often in the subclasses than the point with low value. Now that we have introduced the concept of classes and our new subclasses, we can go back to having multiple classes at once. First, we need to add a third dimension to our illustration. On this new dimension, we can place other class functions, and if you look at the colorized point, new colors have appeared for the two new classes. Now that we have defined the classes and how to extract subclasses, we need to explain the optimization method. We decided to use a mini-batch gradient descent based method. It means that we start with a random point set, and step by step we update the point position to increase the quality of the point set. For each of the iteration of the gradient descent, we want to find the gradient of every point in order to increase the quality of the distribution. We start by selecting one of the class randomly, here for example the blue one, and this class is then filtered at a random threshold to get a random subclass. Now that we have a binary selection of points, the question is where do each point should move to enforce uniformity of the distribution in the subclass. Even if solution exists for this kind of problem in full dimension, it is generally too complex in practice, but fortunately a method exists to simplify the problem. It is called sliced optimal transport. According to sliced optimal transport sampling and some other previous work, it is possible to restrict the dimensionality to 1D problem. Working in a 1D domain has some special properties making the problem easier to solve according to the optimal transport theory. In few words, optimal transport can be seen as the problem of moving a sample from an initial position, here in red, to a desired position in blue, the blue one, while minimizing the amount of displacement of mass. Here, you can see an animation showing an optimal transport between the two distributions. In the 1D discrete case, optimal transport can be solved by ordering the points and the targets along the 1D line and icing them by order. The first point in blue will go with the first target in red, and so on. This property makes the 1D case simple to solve as it only relies on sorting operation compared to an NP-hard problem in the full dimension. Let's go back to our illustration. In order to compute the full gradient, we will need to define a set of 1D projection, like this one. And for each of them, we will project all the points on the 1D line. For the visualization, I will reduce the number of points to 5 here. Saying that we want to uniformize the point distribution along the line, we will need to define what should be the ideal position of 5 points on this line. We start by dividing the domain into 5 parts with equal density in each. This density depends on the projection of density on the 1D line. The different bins here have equal size, but in practice they do not have the same size always. Now that we have the different bins, we want to compute the mass center of each of them, visible as the green dot here. Finally, we will solve an optimal transport matching between the points and the targets, which is done by ordering the two lists and assigning them first target with the first point and so on. This way we can create a shift vector between the points and the target. The last step is to normalize the shift based on the length of the different bins. This way we avoid having a larger shift in the larger bin, and this normalization factor will make a difference in few slides on a comparison. Going back to the full dimension, this shift, which is defined in 1D, can be applied along the 1D projection to move the point. For robustness, this shift is averaged over multiple projections, and the more projections are used, the better the estimation of the shift is. Here you can see few consecutive frames of an optimization when the points are step by step shifted to a better position. Now let's look at a full animation of the convergence of our method. Now let's look at few results. First, I will talk about single class sampling and the comparison to sliced optimal transport from Pauline and colleagues. As you can see, our method shows better distribution with less alignment artifact on the edge of the domain. This can also be seen in the 2D Fourier transform of the point set. Here, the larger the central hole is, the better the quality is. And in addition, the more circular the shape is, the less artifact we have in the distribution. The main difference between the two methods is that we are using this normalization based on the length of the bin inside the projection. For more detail on the difference and more comparison between the two methods, you can look directly at the paper. Now let's go back to the multi-class and the three-class problem I have presented at the beginning. We want to distribute the red and blue point, but also their combination uniformly. If we want to express it using our framework, it would look like this. Two class functions with a staircase shape. This way we have for each of the two functions, two subclasses, the full set and half of the domain. Note that the full set can be constructed from the two classes, so we put it a lower function value for it. This way, it is selected with the same probability than the single color classes. We made a comparison for this problem with the method on Kin and colleagues with the paper Wasserstein blueness sampling. Here, we show three different classes as well as the spectral distribution. Again, the better quality is obtained when the central hole is the largest. As you can see, our method gives slightly better result than their method for this problem. In addition, we can see a small cross in the spectrum that does not appear in ours, how we are able to optimize toroidal point set, avoiding alignment on the boundary of the domain. Let's look at a more complex problem now, the stippling. The idea is to represent an image using only color dots of few colors. Here, we choose cyan, magenta, yellow, and black points. This problem can be seen as multi-class, as we want to distribute the point of different color following their color distribution in the image. For example, here the black and magenta points. But we also want to optimize for the combination of color. here black and magenta, but also every other combination of color. Overall, with 4 different color of dot, we have 15 different class optimized jointly to produce such image. Finally, I will present a last multi-class example, the progressive sampling. The idea is to construct a point set for which we can iteratively add new samples while maintaining a good quality. This type of problem can be expressed using this type of class function. You can see an example here where the new dots appear in red and turn in black. As you can see, the new points appear when we lower the threshold on the class function. The number of times we can add samples depends on the number of steps in the class function. This type of set is particularly useful for Monte Carlo integration, and in few words, Monte Carlo integration consists in approximating the integral of a function, here a 2D step, for example, by averaging the sample of the function. This means looking at some sample position and averaging the obtained value. Two elements determine the quality of this integration, the number of samples and the quality of the distribution. With a progressive sampler, we can play on both elements. To get a better idea, we constructed a multiple progressive set with different properties. First, a single step function covering the entire set. If we look at Monte Carlo error with respect to the number of samples used in integration, we can compare it to a random sampler here in black. The main difference between the two curves is that this one drops at the end of the curve here. This drop appears when every sample are used jointly, which is the problem the set was optimized for. Now, we can choose another function with two different steps, and as you can see, we have two different drops of error as the set is optimized for two different number of points. With a 4-step class function, we can see 4 drops in the error, and the same appear with a 8-step with 8 different drops. More interestingly, our method allows to go to 60,000 steps and 16,000 points. This means we have a step for each single point. In that case, the error drops are supported to be at every single position, making it invisible. Using this set, the result is good for every sample count, but we can also notice that we will not outperform the other sampler for their specific drops in the error. Finally, let me end my talk with the last part on blue noise error distribution in rendering. It's a relatively new approach for rendering, consisting in minimizing the visible or perceived error in rendering. First, to understand how rendering works, we need to see how we produce an image. To produce an image, we need to estimate the color of each pixel of the image, and in the case of light transport simulation, this estimation is done using Monte Carlo integration, as discussed before. This estimation is error-prone, and the error is visible as noise in the produced images that lower the visual quality of the image. This problem can be seen as a multi-class, as we can see each pixel as a class. Here, on the illustration, the horizontal lines show the image plane with 5 different box functions that represent 5 different pixels. The same representation can be made in the 2D domain over the image like this. The vertical axis represents the high-dimensional space where the samples of Monte Carlo integration live. In the blue noise error distribution, we want to include another element, the human perception. The human perception can be simplified as using a Gaussian function placed over each pixel of the image. If we look at the full image, this would look like having a 2D Gaussian over each pixel of the image, like this. For the visualization, I will only keep one of the Gaussians. Note that with this representation, we have one class per pixel, and in practice it means that we have thousands of classes and up to millions of subclasses when optimizing for this problem. If we look at some example comparing a random sampler here with result obtained with our method, we can see that the noise state particular pattern more adapted to the way we perceived it for our method. In more details, the error is distributed as white noise for the random sampler and as blue noise for ours. This is the reason this method are called blue noise error distribution. We compare all methods with state-of-the-art in blue noise distribution with the Abdallah and colleague method and Belcour and colleagues. And as you can see, all method seems to produce a smoother result with less visible noise. We also produce a spectral analysis of this scene, and as you can see in the Fourier transform done per tile, we have a darker and larger central hole than the other method. This difference remains small with Belcour and colleagues, but is present. Now let's look at a specific problem all method can solve where other cannot. Given this scene, we will start by considering the simple problem of a box reconstruction filter. It means each pixel are perfectly independent, as the box function does not overlap, and we want to optimize for this problem. We would result in this kind of image. As you can see, the distribution has no particular pattern and the image looks really noisy. All method makes it possible to replace this box function by a Gaussian filter. This new filter creates overlap between the different classes and help increase the quality of the image. This kind of problem is not possible to optimize using the state-of-the-art method in blue noise distribution, as they only consider independent pixels. In addition to the Gaussian filter, we can also add the perceptual Gaussian over each pixel to increase even more the quality by creating a blue noise pattern in the noise. We made a comparison for this problem with the method and Belcour and colleagues with two different setups. First, a box reconstruction filter and a perceptual filter on the left, and the Gaussian reconstruction and a perceptual filter on the right. First, using a box reconstruction, we have the problem Belcour method is capable of optimizing. In this context, all methods give a slightly better result, but the difference remains small. If we switch to the box reconstruction to a Gaussian, then the difference is more important. All methods maintain a better noise distribution as we consider the reconstruction filter as well as the perceptual filter during optimization. Finally, we propose a scalable framework for multi-class sampling, and in addition to the classes, we introduce the concept of subclasses. It allows us to simply define the complex problem with a limited number of classes associated with non-box class function. As shown in problems such as progressive sampling with only one class function, or blue noise distribution with one class per pixel, we are able to scale to hundreds to millions of subclasses. We also redefine problems such as blue noise distribution as multi-class problem, and using it, we were able to derive new mathematical properties such as an error band. For more detail, directly look at the paper. In future, we want to work on new optimization methods, as currently our optimization is based on a stochastic gradient descent and a lot of estimation of integrals. Even if it helps scaling with the number of objectives, it makes the process slow. We think that other optimization methods could be used, or that reducing the complexity of the problem by fixing some parameter could help getting a faster solution. As we express few existing problems as multi-class sampling, such as blue noise distribution, we think many more could be solved using our framework, and we want to extend the project on this side. Finally, some experiment we made seems to show that it is possible to extend the presented formulation to discrepancy-based metric instead of using optimal transport. This concludes my talk. Thanks for your attention.